Hey everyone, and welcome back to this MasterClass 11 and 12 Explainer. Today, we are tackling some basic concepts of chemistry. Specifically, we are zeroing in on concentration terms. If you've been hitting a total wall with these calculations for your CBSE or ISC exams, you are in exactly the right place. We are going to conquer everything from your basic mass percentages all the way to the dreaded normality. And we're going to give you the ultimate calculation cheat codes in under 10 minutes. No fluff, no filler, just pure high-yield chemistry. Let's get into it.
Okay, let's dive into this like a strategic exam syllabus. We'll start with a quick mole concept recap, then build up to simple ratios and percentages, mole fraction, molarity versus molarity, normality and equivalence, and finally, volumetric titrations.
Section 1, Mole Concept Recap, the fundamental currency.
Think of the mole as the absolute fundamental currency of chemistry. Whether you're looking at exactly 18.02 grams of water or dealing with the 5 basic laws of chemical combination, Avogadro's constant is your non-negotiable bridge. 1 mole contains exactly 6.022 times 10 to the 23rd elementary entities. That specific massive number allows us to translate a real-world mass in grams, stuff you'd actually put on a lab scale, directly into a specific number of reacting particles. Keep this locked in your mind as we move forward.
Section 2, simple ratios and percentages. Dealing with mass and volume parts. All right, here are the crisp, textbook-accurate definitions you absolutely need for your exams. These are all about parts of a whole. Mass percent, or W/W, is the mass of the solute divided by the total mass of the solution multiplied by 100. Mass by volume, W/V, is the mass of the solute divided by the total volume of the solution times 100. Now listen closely, because the biggest mistake students make here is confusing the mass of the pure solvent with the mass of the entire solution. Remember, your denominator is always the total solution. And this brilliantly illustrates that concept in the real world. Think of a 10% WW urea solution, like making a sweet syrup. It's exactly like hiding 10 grams of sugar inside 90 grams of water. You don't put 10 grams of sugar into 100 grams of water. No, you put it in 90 grams, so the final total mass of your sweet syrup adds up to exactly 100 grams. Makes sense, right? So let's step through a classic exam numerical. Say you dissolve 10 grams of sucrose in 100 grams of water. Step 1. Find the total mass. That's 10 grams of solute plus 100 grams of solvent, which gives us a total of 110 grams. Step 2. Plug it right into our formula. Mass of solute over the total solution mass times 100. Step 3, that's 10 divided by 110 times 100, which equals 9.09%. Now, if you had just divided by 100 in step 3, boom, you would have fallen right into the examiner's trap.
Section 3, Mole fraction, the ultimate ratio.
Mole fraction, which we represent with a lowercase x, is the great equalizer of chemistry mixtures. It's simply the ratio of the moles of one specific component to the total number of moles in the whole solution. So x sub A equals the moles of A divided by the sum of moles of A plus moles of B. Instead of measuring mass, which, varies wildly depending on the element, we are now cleanly measuring the fraction of actual chemical particles.
Now, what's really crucial here is the massive exam edge this gives you for both CBSE and ISC boards. First, mole fraction is completely dimensionless. There are no units. Second, it's independent of temperature because it relies on moles, not volume. But most importantly, the sum of all fractions in a mixture always equals exactly 1. So if you calculate the fraction of solute A, you can instantly find the fraction of solvent B just by subtracting A from 1. It is literally a huge time saver during tests. Section 4. Let's move to and see how this builds into molarity versus molality, the classic comparison. Notice the stark contrast here. These are the two most frequently confused terms in Class 11, making this a guaranteed exam question. For molarity, with a capital M, it's the number of moles of solute per liter of solution. Because it uses volume, and we know liquid volume expands when it's heated, molarity is completely temperature dependent. Then there's molality, with a lowercase m. It's moles per kilogram of solvent. Since mass never changes with temperature, molality is perfectly temperature independent.
Let's walk through a molarity numerical step by step. Let's say we have 4 grams of sodium hydroxide in a 250 milliliter solution. Step 1, find the moles. 4 grams divided by its molar mass of 40 gives us 0.1 moles of NaOH. Step 2, always convert your volume to liters first. 250 divided by 1,000 is 0.25 liters. Step 3, divide your moles by liters. 0.1 divided by 0.25 gives us a molarity of 0.4 capital M. Now for an advanced high-yield calculation that links both of these concepts together. Let's find the molality of a 3-molar NaCl solution that has a density of 1.25 grams per milliliter. Step 1, we assume we have 1 liter of solution. Using density, the mass of that solution is 1,000 milliliters times 1.25, which gives 1250 grams. Step 2, we have to extract the pure solvent mass. We subtract the mass of the solute, which is 3 moles of NaCl times 58.5 grams per mole, from that total 1250 grams. That leaves us with 1,074.5 grams of water, or 1.0745 kilograms. Step 3, molality equals our 3 moles divided by 1.0745 kilograms, giving a final answer of 2.79 lowercase m. Pretty cool, right?
Section 5, Normality and Equivalence. I need you to stay highly focused for this one. It's the most complex term we cover.
Normality, denoted by a capital N, is the number of gram equivalents of solute per liter of solution. Honestly, just think of it as molarity, but adjusted for the molecule's reactive power, a concept we call the N factor. To find the equivalent weight, you simply take the molecular weight and divide it by this N factor. Depending on the compound, that N factor could represent its valency, basicity, or acidity.
We're going to rapid fire through this, but you absolutely need to memorize these specific terms because they pop up constantly in tricky exam word problems. Normal just means 1N. Semi-normal means N divided by 2, or 0.5N. Deci-normal is N over 10, and centi-normal is N over 100. Examiners love throwing these exact words at you instead of just giving you the numbers, so make sure you lock these notations in right now.
Let's try it out. Find the normality of 0.63 grams of oxalic acid dissolved in 100 cubic centimeters of water. Oxalic acid has a molecular mass of 126, and its N factor is 2 because it has 2 replaceable hydrogen ions. Step 1. The equivalent weight is 126 divided by 2, giving us 63. Step 2. Gram equivalents equal our given mass, 0.63, divided by that 63, which is 0.01. Step 3. Normality is 0.01 equivalents divided by our volume in liters, which is 0.1. The result is 0.1 N. Now, what's really interesting here is how equivalent weight changes the whole game. If you forget that N factor trap, the whole calculation falls apart.
Section 6, Volumetric Calculations and the Leftovers. Let's tie it all together.
Okay, the ultimate cheat code for titration numericals is the law of equivalence. N1V1 equals N2V2. It's beautiful because 1 gram equivalent of a substance always perfectly reacts with 1 gram equivalent of another. You just plug in your knowns and solve for the unknown. As for the leftovers we didn't spend much time on, just know that formality is basically molarity, but we use it specifically for ionic compounds that don't form discrete molecules. And ppm, or parts per million, is used when you're dealing with incredibly tiny trace amounts of a solute. And that brings us to the end. Mastering these terms ultimately comes down to understanding exactly what goes in the numerator and what goes in the denominator. Make sure you join our MasterClass 11 and 12 Telegram channel right now for high-yield PDF notes and handwritten formula sheets. Hit that subscribe button and definitely drop a comment if you hit a roadblock on any numericals. We're here to help. Also, be sure to watch the full Class 11 Chemistry Some Basic Concepts playlist. Before you go, I want to leave you with a final provocative thought. If temperature changes the molarity of a solution because liquids expand, how exactly do real-world chemical labs account for this during highly precise summer experiments? Think about it, and I'll see you in the next explainer.